Start now. Okay, so as we mentioned, your exam is not this week, but the following week, right? So it will be in lab. You will have all of the lab to complete it. So you get the full hour and a half / 2 hours, right, to do that to do that exam. I might if I give an assignment out that day, it will be one I will probably give you extra time to work on that one. It just depends on the lead up for it. Yeah, probably. Because I feel like I'm moving at a bit of a faster pace than normal. Normally I'm not at, like last semester, we did our exam at week 6, but we didn't have stacks on the exam. So, and here we're doing that. But right now we're going to discuss this. So you've got in the linked list lab. Okay. Please let me know if you need an extension on that, because I'm just going to keep throwing assignments at you. But I'm more than willing to give extension on assignments depending on how the things are turning out. So the linked list lab, the Josephus problem, hopefully that was understandable to everybody, but it shouldn't be too hard. It looks like a lot. Okay, this is the common theme through my homeworks. My homeworks look like a lot, but they aren't actually a huge deal once you actually understand what you're doing. Like this one, all you are doing is writing the add, remove, and get node method, and you already have the get node method, and you've seen the the relevant add and removes in class. The only difference is with a circular linked list, you just have to remember that that when you work on it, the tail of the linked list always has to point to the head, right? So when you add that initial node, your very first node to the linked list, make sure that basically that very first node points to itself, because right, it's going to be both the head and the tail, so it should point to itself. If you forgot that, that's fine. A lot of times the way that people program it, it automatically gets fixed, even though that's temporarily a problem. So once you've got the add and remove, don't worry about the Josephus problem until you've got the add and remove down and you can test it. And you can always test it by using the toString method, because the toString is guaranteed to work. Okay? The toString is guaranteed to work. So if you run it and it gets a null pointer exception, it's telling you that something's wrong. So try it case by case. All right. But as for this upcoming week's homework, well, I finally have a homework for this week, for this subject that's worthy of you guys and worthy of your skills. And that is one that I hope you'll enjoy, because it's one of my favorite topics in computer science, because it doesn't seem like it is. And it's mazes. I love mazes. Mazes are fantastic. They're even more fantastic when I get to this lecture in October and everybody's talking about possibly going to a one of those mazes that are made out of like vegetables or something. This hedge mazes. That's what they are. So anyway, this is a maze. Now my Sunday was fantastic because I came up with this assignment in about 5 hours. About me working on getting the graphics library. Now, part of this, I'll get into what this is in a bit, but the graphics aren't really something, you're going to be working with graphics on this assignment. However, you probably have never learned how to use graphics before, and that's fine. All you have to do is write one method. The graphics library is already available for you, and most of your graphics are going to be changing colors. I will also be putting up a companion video to this assignment to guide you through it, and I'll be writing a method that's similar to what we want to do later, only we're going to be using a queue rather than a stack. So this is a maze. My algorithm for creating a maze is very basic. First, let's just show you what the maze, what my basic graphics library looks like. I'll go into it in a bit, but first, let's just talk about the anatomy. I'll go over this in the companion video, but let's talk about the anatomy of what I've got here and Java stuff in general. So this is what we call a J-frame. This window here that I'm currently resizing, and that's got the X, the expand, the expand and the minimize. This is called what we call a frame. In Java, that's called a J-frame, and that means that basically that it is just a frame to hold all the content, right? It's not really important too much, except that it's for the fact that it holds stuff. And here's like the frame for it. I'm going to give it a new name rather than maze test, because when I was writing it, it was a test. This dot add the new maze grid panel. That means add all the nice, cool-looking stuff to actually hold it, right? Then it says set the size to 800 by 800. If you can guess, that means I'm just setting the size of my frame to 800 by 800 pixels. Nothing too scary there. This one just means set default operation on close. That means if I actually hit the X button, if I actually close this window, the program terminates. It doesn't keep running in the background. pack it all up for the user and make sure the user can actually see it. Right? That last one kind of makes sense. You want to be able to see it. Okay, that's really all it does. And then I just call it a main, right? I do new maze test. And notice that I can do that and I don't actually save it in a variable because it's going to exist until I hit close on the window. Okay, so now when I run this, I created a new maze grid panel, as I called it. Now a panel is basically the basic stuff in Java that we get for like putting content on it. Right, a panel can hold buttons, which it doesn't have any here. It can hold, text box. It can hold dialog box, none of which are here. Panels can hold anything they want, including other panels, which is what we've got over here. So this is one big panel that holds a bunch of panels that I call cells. Right, so see how it's just a grid? All I've done is just create a grid. Okay, and what's useful about this? Anybody know how like pixels are how pixels are working in programming? So most of the time you work in a coordinate plane, right? So on your computer there is a little display that basically changes colors for you. And we need to be able to control those things. Now controlling those one by one is tedious, but you could do that. Instead, typically we let the library do that for us. But the end result is that those pixels have a location on screen. They have XY coordinates. Typically, though, we don't work with the typical coordinate plane that we work with. Instead, we work with this coordinate plane, which is positive x and then y over here. So this top left corner is 0, 0. Okay, makes sense to everybody? Now, this may seem confusing, but remember that for an array, right? If we were doing a 2D array, this would be at 0, 0, right? And this would be at 1, 1. This would be at 2, 2. Right, so it meshes up exactly with the way you expect arrays would work, which is partially, I guess, the reason why it's done that way. Furthermore, basically each of these panels holds the coordinate plane internally to itself. So this is 0, 0 for this little cell. This is 0, 0 for that little cell. This is 0, 0 for that little cell. So it makes it so I don't have to do math. But anyway, enough about cells and how does that relate to mazes? Okay. Well, a cell is a pretty simple little guy. They have 4 walls, which I initialize to true, and then they have a row column, which is just simply its location in the maze. Okay, and all this does simply is I say basically get the height and width of the cell. And if you've got a north wall, we draw a wall along the top. If you've got a south wall, we draw a line along the bottom. If you've got an east wall, we draw a line along. This is all stuff you don't need to know, but I'm just showing you to explain how this works. Okay. And all I do to create the maze is this is the only relevant bit of graphics you need to know. What I do is that I set the background of the square equal to white, right? And then I initialize everything to true, so it has everything. Now, how do I actually create the maze? It's looks long, but it's not so bad, and it's easier to explain it with it up. So let me go ahead and run So here I am initializing the grid panel. I say, please set it to 800 by 800. Set the rows and columns equal to rows and columns. I'm going to be adding stuff to it. So if you could please lay it out in a grid, lay it out in a grid for me. And then I create a array so that I can access my cells, each of the cells I create pretty easily. And then for every single cell that I want to create, right? So I wanted to create, when I run this, I'm creating 20 by 20. So I say, for each row column in this array, create a new cell and add it to the grid. Okay, fairly straightforward. I'll be reviewing this in another video. Okay, and then how do I generate my maze? I generate my maze by the first thing I do is that if I'm in the 0th row or the 0th column, well, if I'm in the 0th row, I remove all the east-west walls. Okay, everybody see how along the top all the walls have been removed? And then if I'm and then for this guy, for column 1, I remove all the northwest walls for column 0. Okay, and then the maze is generated fairly straightforward. This is one of the stupidest algorithms out there, but it's not the stupidest. It's actually clever, but it's just dumb. What it does is that basically for each cell, it flips a coin. If we look at our logic here, if we look at my logic here for generating the maze, for each row and column, if it's the top left guy, I don't bother going over him. I just skip him over because he's because he's not relevant. For the first row, I eliminate the west wall and the east wall. And for each, if you're in the first column, I would take away both your north wall and south wall. Otherwise, I flip a coin. If it lands on heads, I remove your north wall and the guy above you, his south wall, right? If I'm removing my north wall, then in order for there to be a line not drawn, I have to remove the guy above me, south wall. And then for everybody else, I tell them, if it landed on tails, I say I want to remove my west wall instead, and the guys to the left of me, his east wall, right? Right. So I remove my left wall and I remove my neighbor's right wall. Okay. And so as a result, right, this guy decided to remove his west wall. This guy flipped and he removed his north. This guy removed his north, west, and so on and so forth. And we just did that for the entire thing, and now we've generated a maze, right? And the goal of this maze is to get from this corner to this corner, right? Find a valid path. Now, this isn't the best maze generating algorithm because for everything I'll generate, every single puzzle I'll generate, it's always going to be like some path that I always go down and to the right, right? There's not going to be any winding corridors with this. But for right now, just for our objectives on what the homework actually is going to be, this suffices. Now, our homework will be solving this maze, writing something that actually finds our way through this maze, like so. And in case you're wondering how long it took me to go from the white maze, from the just complete blank maze to about this, it took me maybe half an hour to 45 minutes. And that was just making sure I was doing everything okay, and I didn't have anybody explaining this to me. Also, for full reference, I basically have forgotten everything I ever learned about doing Java graphics, and I relearned it all with enough to do this on Sunday. So it's not really as intimidating as it sounds because I was able to just put this together in a few hours. Okay, and your objective is just doing this part. So why is this gray? Well, this gray denotes what I've already visited. The green path is a valid path. Now the maze is randomly generated each time, so it doesn't matter. It just always finds a path. And this works for mazes of basically any size. Now it starts getting slower once I get above 100 by 100 size, but just because it takes so long to generate. But it works for fairly large mazes. Okay. Now you're wondering, okay, why? What's the point of this? I thought we were learning about stacks, and now I'm learning about mazes. So let's talk about how we solve mazes for the first part. So let's talk about the way to solve basically any maze, including this maze. And this is called the right-hand rule, which is different from the right-hand rule of engineering. Okay, which is that suppose this is the entrance over here, and that is the exit of the maze over there. And all these desks are walls. Okay? The way I get out of this maze is I slap my hand onto the right wall, and I don't let go, and I just walk. And so long as the entrance and the exit of the maze share a wall, you're going to get out of the maze. Think about it for a second. I'm just going to simply go along this maze, and then when I get to that desk, I'll simply go along the desks, then go down back, then go along and go down back, and simply I'll just find my way out here. This isn't a particularly sophisticated maze, but it suffices to show that the right-hand rule algorithm works, which is just simply if you go down a bunch of corridors and just keep going right, you'll get out eventually. Okay? Now, this doesn't work for every maze, though. It only suffices if your exit is like there. Suppose like the exit was like an elevator in the middle of the classroom, right? Or something like that. Then the right-hand rule would never get me out of there. So there we need to rely on a more tried and true method, which is called recursive backtracking. So because we're going to get into recursion today. But today's assignment doesn't actually use recursion, except it totally does, except some might argue we don't use recursion because we're not going to use method calls. I know it gets confusing. Today we're just going to use stacks. But let's keep to our actual maze solving in actual person. Okay. So you really to solve any maze you need just two tools. Okay. The first tool is chalk, the mark off corridors you've already been on. okay? Because you don't want to go down a corridor you've already explored. If you go down a corridor you've already explored, you're just wasting time, okay? No need to loop back around to do that. And the second thing you need is a giant ball of string, okay? Basically, so take, and maybe some hammer and nails so you can hammer the string in at the entrance when you enter the maze, okay? And the idea here is that with it, what I'll do is that I will simply, as I travel, unwind this string, right? And then if I get to a choice, to a place I need to go, I go down that corridor and I mark it off to make sure that I know that I've been down that corridor. If I get to a dead end, right? And by a dead end, I mean somewhere basically like a traditional dead end, like, oh, there's walls all around me, there's nowhere to go from here. That's fine. What I do is I back up. But there's another type of dead end, which is that what if I come to a place where basically I've noticed that I've checked off all my, there's a corridor here, there's a wall here, but I've been down that corridor already. Well, I know not to go, well, there's no reason to go down it again because I've already been there. So I simply, in that case, backtrack. I use the string and wind it back up to get back to where I am. Okay, so so what are our two tools in programming terms? Well, the chalk is this coloring that we're doing over here. Okay, so what I do is that basically, the path I'm currently on, I color it green. And if I have to backtrack, I'm coloring it gray. And anything that's colored white, I haven't been to. I also happen to color my, when solving this maze, I happen to color the ending spot red, so that I know I would get, if I got somewhere red, it was the exit. But that's, I'll show that off some other time. The idea here, though, is that basically I use that. Now, what about the ball of twine? How do I back up? Well, the idea behind this is using a stack. Okay, so I'm going to use a stack. And the idea here is a fairly simple algorithm, which is that if I go down a path, right, every time I move into a cell, right, let me go ahead and change this because it's easier to show if I do something like a 5x5 maze. So not a particularly hard maze to solve, right? So, okay. So the idea here is that basically, what commands can you give basically a robot to solve this maze, right? One that can't really intuit stuff. Well, the idea here is I'm going to use a stack. So I'm going to start here and I want to get to this corner. So what do I do? Well, the first thing I do is I pop this location, I push this location onto my stack, okay? And while my stack is not empty, okay, so as long as I have stuff in the stack, and so long as I haven't finished the maze, right? So if I've got an empty stack, that means that basically that the maze is unsolvable, so no use in continuing. And if I get to the end, well, I might as well stop, right? No sense in exploring a maze since I've done everything I need. I need to explore. So how do I explore? Well, the first thing I do is I have 4 cardinal directions to go into. I can go north, south, east, and west. So I ask, can I go north? Well, no, I cannot. Can I go south? Yes, I can. I can go south. Have I been south? No, I haven't. So I'm going to go there. So if I can go south and I haven't gone south yet, go south. And how do I go south? Well, I push that location on top of my stack, and then I go back to the top of the while loop, and I peek at the top of my stack to see where I currently am. Okay, that makes sense to everybody so far? So I peek. Can I go north? Well, I can, but I've already been there, so why bother going? Okay, can I go south? Yes, I can. So I push that on top of my stack, peek at the stack to get to the top of my place. And by the way, as I'm going, I'm coloring all these locations green just to make sure that I know that I'm there. Been there. Okay, I go this way. I go south again. Can I go north? No, I cannot. I've already been there. Can I go south? No, I can't. There's a wall there. Can I go east? Yes, I can go east. So I go east, push that on top of the stack. Can I go north? No, there's a wall there. Can I go south? Nope. Can I go east? No, there's a wall there. Can I go west? Well, I've already been there. That'd be going backwards. So I'm at a dead end, right? I've tried all 4 cardinal directions and I can't go anywhere. So what do? I pop my current look. I set my color. I change the color of my current place to gray from green, and then I pop on top of the stack. Now I'm back at the top of the loop, and I say, okay, I'm here now. Can I just repeat my steps? Can I go north? Yes, but I've already been there. Can I go south? No. Wall. Can I go east? Already been there. It's gray. It's been visited already. Can I go west? Nope, there's a wall there. So pop, and then I make the same decision here. Pop off the top of my stack, get the current of the stack, pop off the top of the stack, get the current of the stack, pop off, I'm back at the beginning, and all this has been colored gray. Okay? So now I'm back here. Okay, can I go north? No. Can I go south? Already been there. Can I go east? Yes, I can. So everybody see how it continues like that? This is what we call recursive backtracking. Basically, it continues until it gets to a dead end, and then continues forward. Specifically, this type of searching is, does anybody know what this is called? This is depth first search. This is depth first search. And this means that basically I am going to be exploring a tunnel basically for as long as I can. And then once I hit a dead end, I back up and explore the nearest tunnel I can find. Okay. What tools will you have at your disposal for this? You will have a generate. So let's see. I give you basically all the code here except for this solve maze function over here. You get everything but the solve maze. And I even give you the visited, and I'm going to give you even this as a guide. The solve maze using the queue, which uses breadth first search instead of depth first search. So basically your code is just going to be missing this thing. And even this, I'll give you a bit of code to start off. There's a visited function, by the way. Check row. Have I visited row column? I get the background of that row column cell. If it's white, or it's red, I haven't been there, so I return false. Otherwise, if it's any other color, return true. Red, again, I'm using red for the exit. Okay. So that's pretty cool. You can use stacks to generate mazes. Oh, sorry, to solve mazes. You can also use them to generate mazes. In fact, you can use the same algorithm to generate a maze, just with a few tweaks. And the extra credit will be making my maze generating algorithm better. Because I don't know what the difficulty of this assignment is going to be. So let's go ahead and look at some maze generating algorithms. Right? If we look over here at the recursive backtracker for generating a maze, make the initial cell, the current cell, and mark it as visited. While there's unvisited cells, if the current cell has neighbors which have not been visited, randomly choose one of your neighbors, push it onto the stack, remove the walls, and then make the chosen cell the current cell and mark it as visited. Else, if your stack is not empty, pop it and make it the current cell. So basically, if you can go somewhere, you go somewhere and push it on that location onto the stack. If you can't go anywhere and your stack isn't empty, pop the cell. So this is very similar to the algorithm I just went through, right? Let's see it in action. This is a hex maze, but this is what it's doing. It's simply going around, choosing neighbors, removing the walls, okay? And then once it hits a dead end, like it did just there, okay, and I paused the video at the right time, which is pretty awesome. It goes, okay, I'm done. So I need to back up to where I can find a place, right? I'm still at a dead end, and then it goes out, finds itself into another dead end, backs up. So see, basically, green is where it's backed up, and it's, done, essentially. So it eventually will generate a much more windy maze than what I've got, than my algorithm does. Mazes are these whole cool things that are awesome for research, because from a robot's perspective, getting around, almost everything's a maze. So this has some really cool AI applications, and this is kind of an intro to that. But it's what's fascinating is the only tool you need to complete this is a stack. So that's your homework with regards to stack. It's not as hard as it sounds, because once you figure out how do I go north, you just copy and paste it for south, east, and west, and just modify. Okay, so north is -1, so south is +1, and then you guys will see when I code it up for the queues. Okay, so let's go on and continue with our lecture, and then we'll go back to the mazes. Right. So we could. So when we left off, we were talking about computers and doing math and not wanting to get into Facebook fights, right? Specifically, the Facebook fight was, 9 out of 10 Americans can't, correctly solve this math problem, right? and where basically they give you something where the order of operations might be ambiguous because, believe it or not, there's different sources that say you should do different things depending on whether the divide, what symbol is used for the divide sign. So computers don't like ambiguity, and they probably don't appreciate Facebook fights. So instead, we're going to use postfix notation, which all you need to evaluate that is a stack. You don't need parentheses or anything. You just need a stack. So let's go ahead and then see how this works. The idea is that for each of these, if it's a number, we just when we evaluate this, we create a stack, and then if it's a number, we look through this. If it's a number, push it onto the stack. Okay, so here I would do push 4 onto the stack, push 7 onto the stack. Okay, and then once you hit an operator, any operator, okay, you pop twice. The first pop is going to give you the right operand. The second pop is going to give you the left operand. So I'm going to go ahead and do these on the board. Okay, so just so that we can see how these work. And then once you pop them, you evaluate those two expressions and push the result back onto the stack. When all is said and done, there should be only one thing left in the stack. Look at the top of your stack, and that's your answer for the entire expression. So put 4 on top. Sorry, put 4 in the stack. Put 7 in the stack. We see a star. Do pop operation. Do one pop operation to get the left. Do one pop operation to get the right. Multiply them together because that was the operation, and push the result back onto the stack. You get 28. Okay. What about this one? We know the equivalent is 4 times 7 plus 2 in parentheses. Well, we don't need any stinking parentheses for these things because it's completely unambiguous the way it works, right? The rule is push stuff onto the stack and pop stuff from the stack. So push 4 onto the stack, push 7, push 2, you find a plus. Pop 2, pop the right operand and the left operand. 2 and 7. 7 plus 2 is what? 9, right? So we pop and then we push that back on the stack. Making sense so far? Now that we see a star, so we did push, 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 pop, pop, and add, and then we push the result back onto the stack. And now we see a star, so that means pop, pop to get your right and left operands. So 9 and 4, and then put the resulting thing back on the stack, 36. And take a look at the top of your stack. That should be your answer. We'll go ahead and skip and go ahead to the bottom one. Okay, so 3, 4, 7. Okay, then times. So now times. So we pop and we pop. So we get 7 and 4 multiplied together. That's 28. We put that back on top of the stack. Okay, so we did 3, 4, 7 star. Now we have 2, and then divide. Now remember, the right operand comes off first, then the left operand. So it's 28 divided by 2. So then that results in 14, which we push back on top of the stack. Okay, and then we do plus, which would be 3 plus 14. Pushes 17 on top of the stack. And we've got 17. So this is completely unambiguous. It's weird to look at, but that's okay. So this is what we call postfix notation, also known as reverse Polish notation, because it's the reverse of Polish notation, which is another unambiguous way to do these things. In Polish notation, rather than doing 4, 7 plus, you would do plus 4, 7, which seems weird. Until we do it something like this, which now it looks like a function call, which basically it's saying this is the function. You put the function you want to use and then the arguments for your functions for Polish notation. And this is reverse because it just happens to be the reverse. So, and then we've also, of course, got graphics to explain that. So you can use, so again, very simple data structure doing very interesting things here. So we just simply create an empty stack of integers while there's more stuff to get. 4 goes in, get the note. Sorry. So if the first character of the token is a digit, push it onto the stack.
that's a digit, so we push the token onto the stack. Times is not a digit, but it's an operator, so we pop for a right operand, pop for a left operand, combine them, push it on top of the stack. Okay, put 20 on top of the stack and subtract now. So it would be 28 minus 20. Push that result on the stack, which is 8. There's nothing left, so we pop the stack to get the result. Okay, and it was honestly either this as your assignment, writing something that did this, which was specifically converting from infix to postfix and then evaluating the math expressions, or the maze. And the maze honestly sounded like a heck of a lot more fun for you guys. So even if it does look slightly intimidating. Okay, so that's actually our result, the end of our lecture on stacks. That being said, that's not the last we'll see of them, because when we talk about recursion, we'll be talking about the stack as opposed to a stack, which is the stack that your program uses. That we use to actually keep track of where we are in the program. So with that, that was stacks, and I told you that the chapter on stacks would go by really quickly. We're going to talk about queues now. It's pronounced Q, so the first letter, and then you just forget about pronouncing the rest of the letters. Okay, so it's not too hard. So queues, as you may know, are like basically that term for line in more commonwealthy nations. So people don't line up; they queue up in Britain. And now that you know that, if you didn't before, now you can pretty much understand exactly how a queue works. It's a line. Or if we're going to use a much more formalized term in computer science, it's a buffer. Okay, which means that basically that it's first in, first out. Okay, we're going to look at basically, it's pretty easy to see how we can use a linked list and a doubly linked list to do these things, but we're going to talk about a circular array because they're cool and worth mentioning. And a lot of times I'll do that in class. I'll go over it in lecture, and just so you can have exposure to it. So stacks and queues are often taught together because they are the reverse. Stacks are last in, first out. So the last thing to go into the stack is the first thing out, right? We always remove the top of the stack. But a queue is a first in, first out kind of data structure. The first thing so the first person to get in line for that Disney ride is the first person who's going to be on that Disney ride, right? And everybody else has to wait their turn. Okay? Right? And as a result, basically, if you've been in the queue the longest, you're the one getting served next. Okay? So an idea, and this is useful because a lot of times you want to model stuff and you're not going to want to use a stack, right? Here's a print queue, which is a queue that your computer has that you've probably interacted with at some point in great frustration. So it's especially useful like when you're at the library or something, where basically somebody's you're trying to print one page and the guy ahead of you is printing their end of term project, which is like 30 pages. Okay, and really you would just like to get home. The idea here, though, is that a queue allows people to line up and use some kind of scarce resource, right? So for us, when we're being entertained at like an amusement park, it's that ride. That's the scarce resource, the seats on the ride. For here, in this case, it's the printer, okay? And for people coming to a website, it's basically, who can I make a connection with, right? So a queue is just basically a way to enforce, kind of a fairness kind of deal. And you don't want to use a stack for this kind of purposes. Why don't you want to use a stack? Well, because the first person to be served is the last person to make the request, the person who's waited the least. And that means if you're actually the first person to come in and somebody comes ahead of you and somebody comes ahead of them, you might not even ever get served. Or even worse, you might be the game theory type of person who realizes that if you're dealing with a print stack and you try to print something, but then somebody tries to print ahead of you, right? Then what do you do? Well, I want my thing printed first, so I'm going to print now, and then they're going to print, and so now you get into a printing arms race to see who can basically because you're all going to just keep cutting in front of each other, right? So you don't want to print stack because just sometimes because a lot of times queues are just the most fair way to do things. The person who's been waiting the longest, or the process that's been waiting the longest, gets access to the resource. There are also things called priority queues, which we'll talk about when we get into heaps. And with priority queues, that basically allows people to cut on the line, right? And that's useful because, like, in taking for example, the situation in a hospital, right? You've got people who have come in with maybe a broken finger. That's painful, but it's not urgent like somebody coming in with a heart problem, right? So while you're in line, right, the people who come in with like more severe problems that need to be treated sooner, otherwise they're going to die, they cut the line. They're higher in priority. But you're going to be seen before everybody else in your same urgency level, right? If you come first, you'll be seen before all the other people with non-threatening broken limbs or something like that, okay? This is the entire point of triage, by the way. The entire point of triage is to basically say this person needs immediate medical attention or they're going to die. This person can suffer and wait for a little longer because they're not going to die. It's going to suck, but... And that's the entire point of pre-triage. And that's why a lot of times when you go to the hospital, you have to wait because it's not really because it's not as important as that infant coming in who's got a fever of over 100.1, right? So, but right now we're dealing with queues where we don't have to cut in, okay? Also, as we'll see, is that we can use a queue to do something called breadth first search. Stacks are useful for if you want to go down a tunnel as far as you can and then back up. A breadth first search is basically if you want to scan basically and slowly go through it one at a time. So basically I want to explore 1 step down each corridor, then 2 steps down each corridor, then 3 steps down each corridor, then 4 steps down each corridor. It's a slow way to do it, but it's a feasible way to do it. And it's actually useful in some things. And we learn way more about that in chapter 10, but I'm actually going to go over it here. So let's go ahead and get into the specifics of writing a queue. The queue is an interface, unlike the stack, which is a class, which means you cannot actually make a queue in Java without just like you can't make an actual list in Java. Instead, we'll implement it with something else. But it does offer 4 methods. The first is offer, which is the add method for a queue. It offers an item to the queue. I sometimes call it enqueue because honestly that's a better word for it. And that basically says add this item to the back of the queue. Make sense? So offer the queue to add it to the queue. This next I'm going to skip remove because I'm not going to use it because it's pretty much the same as poll. P-O-L-L. We poll the queue to basically, this is the equivalent to the pop operation here, where we get the front item from the queue and return it. Okay, so poll, sometimes you hear it called DQ, right? So NQ and DQ. And if you use that terminology, I'm not going to be mad. That's perfectly fine. I'll understand exactly what you mean. So offer, NQ, poll, DQ. Offer to add put something on the back, put something in the back of the line. Poll gets the thing off the front of the line. Then you have peek to check who's at the front of the line, which is the same as element, so I'm not even going to bother talking about element. And then, of course, you can check whether or not it's empty. Right? So the way you typically create since it's an interface, the way we create it is like if you want to create a queue of strings, then you create a linked list of strings. And it's pretty easy to see how the linked list provides a way for you to use a queue in constant time operations, right? To poll from the queue, you remove the head of the linked list, right? And that's a constant time operation. To add something to the end, you're just adding to the end of a linked list, which takes a constant time operation so long as you have a tail, right? But as we've discussed, let's see, So as we've discussed, basically, the idea here is that we can do constant time operations, but sometimes it's space inefficient to do it like this, okay? The idea here being, remember, when we were talking about queues, the idea was, when we were talking about linked lists, is that basically the next and the previous of a linked list, those take up space, right? So instead what we need to, if we don't want to use that up, we could use an array. But the issue with an array is that while we can add to the back of the array in constant time and remove from the back of the array in constant time, adding something into the middle or the end, right, we have to shift everything over. Really, we don't have to care about the middle, right? Adding something in the middle or the front, we have to shift stuff over. But here we don't have to really care about adding stuff to the middle, just adding stuff to the front for a queue. So instead, what we're going to do is something called a circular array, or a circular buffer as it's called. And to be honest, now you may be wondering why I'm talking about this, if I'm not really like going to include this on exams or anything, because I'm not. And the answer is because I found it very useful when I've had it come up a couple times during interview questions, or and practice interview questions. So this is a useful thing to know when you're trying to deal with basically you're saying your only resource you can use is an array, right? But we want you to do these operations efficiently. So the idea with a circular array is that basically that we're going to add stuff to the end of it, and then remove stuff from the front, and then we update what index the front is. So how do we keep from wasting the space that basically we removed? Well, the idea is that we wrap around. So rather than coding it out, we're going to just watch. They've actually gotten the slides on this one are actually amazing, which is part of the reason I like going on this one. So suppose we're creating an array queue, right, as opposed to a array list. So an array queue of size 5. The idea here is that we're setting it up with initial capacity of 5, right? If you remember, so capacity works the same way it does an array list. We create an array to hold the stuff in. We say the front's located at index 0, and the rear is at capacity minus 1. The capacity is 5, so rear is at index 4. Okay? Right now it's empty. And of course the size of this is equal to 0. Remember, the size is the total number of stuff in it. The capacity is the number of stuff we can fit in it. So now, let's see how offer works. Okay, to offer something to the queue, if the size and the capacity are the same, right? If we're out of space, we're going to reallocate, right? So we don't have that to deal with that now. We'll see how that works at the end. Otherwise, we increase the size by 1 because we're adding something to it. And now, we say that the end of the list, end of the array, is located at rear plus 1 mod capacity. So it's the modulo operation that's actually going to do the magic over here. Because, so let's look at that. Rear is currently 4, so rear plus 1 is 5. Mod 5 equals 0. So now the rear is at index 1, and now we add this item to the back of the queue. We add it to index 0, and we return true. And this makes sense for the first item. The front and the back are both the same. So let's add another item. Add the plus sign. Well, we increment the size by 1, so because there's going to be 2 things in there. Now where should the back be? Well, it needs to be at rear plus 1. And then we do mod capacity to make sure we aren't, as we'll see, that will help us when we need to wrap around. So then we store the item at that new index, right? So now we've got a slash, we do the same thing. Increment the location of rear, put the item at that index, and return true. So same thing for this one. And now we're going to add our last item, A. So we've got add 5 elements over here. Right? We only are going to reallocate when we're trying to add something and we're already full. Okay? Now let's see how removal works. Pull. If the size is equal to 0, return null. Well, it's not an empty list or an empty array. So instead, we're just going to grab our item from the front, right? That's what this one does, grabbing the item from the front. And then we say the front is located at front plus 1 mod the capacity of the list. So we move the front, we increment the front, and decrement the size. Okay, so now here's where the modulo operations really become magic. Okay, so the idea here is now that when we're pulling, right, we're going to just pull again so that we're over here, so that we remove the star and the plus sign. So now here's where the magic happens. Is the size equal to the capacity? No, it is not. So we don't need to reallocate, right? We've cleared space. We removed the star and the plus. So increment the size to 4. The rear is now rear plus 1 mod capacity. So it's equal to 4 plus 1, 5, mod 5, which is 0. So rear is now 0. Now store the item at index 0. So now we overwrite with B. Overwrite. And now here we increment rear by 1 and overwrite this with C. Now, and that's basically how it works. If we were to do three pull operations, front would wrap around over to here. So basically, by using modular arithmetic, we really get the chance to wrap things around. Now we'll go into a lot more about this wraparound operation when we talk about hash tables. So it's a good thing we introduce it here. Yes.
So pool does not, that doesn't really remove the
I'm no more than removing an item from an array list removes an item from an array list. So here, when we actually need to reallocate, we start from the front and wrap around. And basically, so we start at front and we move each of the items over into here, and then wrap around and basically grab all the items. And how do we wrap around? The mod capacity ensures that we wrap around. And then we just set up our front and rear appropriately. Okay, so that's pretty cool. And we talked about, and so let's go ahead and see though how we can use a queue to go ahead and solve our maze. Okay, so the idea here is that we're doing a breadth first search rather than a depth first search. Okay, I'm going to rewrite this code, by the way, in front of you, so you don't have to like copy it all down all at once because that would be boring. But I'm going to go ahead and write the solve maze queue. So in order to see the full effect of it, it's not looking for the bottom right corner. It's looking for like 5 up from the bottom right, because otherwise it wouldn't look. Oh yeah, that's not going to work for it. That's the start and the end in a 5 by 5 maze is going to be the same thing. So let's look at a 20 by 20 maze. Okay. So okay, we've got new things going on here. So it stopped over here, because that was the stop location for it. But what are the blue things? Well, what these blue things are these are the items currently in my queue. These are the cells that are currently in the queue that I'll be visiting next. Right? These are what I have to visit in the future. So here, I'll visit this one next, then 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 I'll visit this one next, this one next. So this one isn't so much a robot as it is like a flood going across the screen. Okay? Because remember, with the recursive backtracking, we were imitating we were a person. Here we're imitating we're pouring water down, and from where we're starting and letting it flow to the exit of the maze. And that's just simply because your computer can teleport, whereas you can't. So let me go ahead and set it up. All right. So the first thing I'm going to do is I'm going to create a queue to solve this problem. So you're not going to want to follow what I have is going to be very similar to the stack problem, but it's going to differ in some significant ways. For one thing, I'm going to be using a bunch of if statements and your stack is going to be using a bunch of else if statements, right? If I can't go north, then try going south. Here, I'm going to check all my neighbors and try to go in all those directions. You'll see what I'm talking about. So queue to visit next is equal to a new linked list of cell. So this is what we're doing is breadth first search. The idea here is I'm visiting, basically, if you imagine you want to look at basically your friend network on Facebook, if you have Facebook, right? A breadth first search says, all right, I'm going to look at myself. Now I'm going to look at all the people I'm friends with. Then I'm going to look at all the people that my friends are friends with. And then if I go out one more circle, it's the friends of people who are friends of people who are friends. Anybody play the game 5 Degrees to Kevin Bacon? Yep. And surprisingly few people are actually saying. So the idea here is that that basically Kevin Bacon is extremely he's going to appear in a lot of things. So the idea here is that you can go from 6 degrees. You can go from one actor to Kevin Bacon in about basically 6 steps. Basically from saying this actor performed with this actor, who performed with this actor, who performed with this actor, who performed with Kevin Bacon, essentially, and saying. So the idea here is that actors have a Bacon number, which is basically how. So if you've acted with Kevin Bacon, your Bacon number is 1. If you've acted with somebody who's acted with Kevin Bacon without actually acting with him yourself, you've got a Bacon number of 2. Okay, so that's kind of what a breadth first search is. Okay, So, to visit next, so let's go ahead and get our create our starting location, which could be anything, but I'm going to say it's the cell at location 0, 0. So, and to denote that it's the start of our maze, I'm going to color it. Start dot, and the way I color something in this is I say set background. And this sets the background of that cell to, so the lines are on the foreground that we draw, but this is on the background. So set background is equal to, and then I say a color dot, and then there's a list of what I can do here. If I don't like any of those colors, by the way, I can do new color, and I can give it 3 arguments, red, green, and blue, right? To say how much red, how much green, and how much blue I would like in there. But for right now, we'll just go ahead and say I'd like a new, I would just like, let's say my starting location is the color cyan. Why not? Okay. And then my finished location, I'll say that it's the number of rows I have minus 5 because I want minus 5 because I want it to be not at the bottom left corner because otherwise we're not going to really see it work. And that will be your finish. And that's our exit for the maze, right? And the idea here is that we will go and look at and say finish. And this is the way I'll be setting this up for you in your homework. Set background to color.red. So now if I run this, right, here's my start, here's my finish, there's my exit, and I want to get there. Okay. Now the way this is going to work, because of the way this all, I'm always removing the north or the west wall, right? It's always going to, the paths are always going to go like in a curve in this just manner. So it's almost going to always look like it's exploring like a flood diagonally across the screen. So so the idea here is now I've got my start location. And now a queue, and that's where I want to start. So I'll say to visit next dot offer my starting location. Okay, right? Because obviously the first thing I'd like to visit is my starting location, right? Make sense? Boolean, and I'm just going to set this up. Done is equal to false. So while I am not done, and my queue isn't empty. So to visit next dot empty. So dot is empty. Not. So basically, while there's stuff in the queue and I'm not done, I'd like to keep going, right? So first, let's establish how do I know when I'm done. Well, the first thing I have to look at what I'm visiting. So the current cell I'm visiting is equal to visit next dot pull. Now this is where I'm going to differ from. This is where we start differing from the stack-based method. In the stack-based method, you're going to peek. You don't remove it. In here, we're going to remove it. Why don't we remove it in the stack? Because in the stack, we basically got to keep, because we want to keep it for backtracking purposes. Here, once we visited something, we visited something. Okay, so I'm going to call this current. So instead of cell, so if current is equal to my finish node, so a finish cell. So in other words, if I made it to the end of the maze, then done is equal to true, so I'm done. Otherwise, I need to try doing a bunch of other stuff instead, okay? Otherwise, let's see where I can explore. And so the logic is actually going to be quite different. It's going to be similar, but different for the homework you do. The point here is to get you familiar with the dimensions in the maze, okay? Which is, north, south, east, west. So otherwise, let's look at the locations I need to visit to add them to visit next. Let's consider the north first. So if current dot north wall, right? So if I don't have a wall to the north of me, so not north wall, and so in other words, if there's something that I don't have to the north of me and visited, that's a function that I wrote for you guys. This dot visited, let's see, current dot row -1 and current dot col. Let me go ahead and minimize this because the line's starting to, whoops, the line is starting to get quite long. So you might be wondering what the heck at this point. But what this is saying is that, okay, if my current cell does not have a north wall, right, and my and the thing to above me, right, at my row, but one row above me, that's what -1 means, and I'm in the same column as me. So basically, the cell to the north of me, if that has not been visited, then I would really like to visit it. Okay? So how am I going to mark it as visited? I'll say that to visit next dot offer. So what do we need to offer? Well, the one to the north of me. So that would be maze row -1 column, right? Add that to the maze, and then we're going to say that that's now, we're going to mark that as green so we don't add it again. Oops, sorry, not row -1. Current.row -1 and current.column. Okay, and then let's just copy paste this guy. And say, let's ask to set his background color set background to color.green. Okay? So that was just what we had to do for the north. Now you may be thinking, oh god, there's 3 more directions. And I'm thinking, yay, there's only 3 directions to do, because what I'm going to do is that I'm going to do this. Control-C, Control-V, Control-V, Control-V. Okay? And now it's actually fairly trivial to do. South wall, and then what's the south of me? That's +1, not -1. So row +1. So now I change all these to +1 and +1 over here. Okay. Otherwise, let's say one of the east wall. Sure, let's go east. What direction is east? East is to the right of me, right? So that's in the same row, but it's in column +1. Whoops, 1, not 2. Column +1. And then west wall, that's the last thing that we need to do. West wall, well, that's column -1. Okay, so let's see what happens. So we do all these things, add them all. Let's see what happens now. It works. We get from our start, and then we hit our end right over here. And now let's go ahead and change this up slightly, just to make it clear, because basically green is everything we're visited. Now, once we're going to change anything that we've already been to blue, right? Anything that we're done with, that's currently out of the queue, to blue. So current dot set background to, oh, that's border. So set background to color dot blue. anything we've already traveled to will be blue now. And then anything that's still in our queue is now green. So this is, again, this is a breadth first search of the maze, where basically you go down one step. So the way it works is that I'm going one step here and then one step here. Then I'm going one step here and then one step here, and then one step down here. So it just simply visits. It essentially just is another methodical way of going through it, although it does take a bit longer. There's more stuff that gets visited.
Is it just going in every direction?
Yes. Yeah, pretty much going in every direction at the same time, essentially. It's as if you have multiple people who can run through the maze and every time there's a split, you tell them to go off at the same you tell them to split and continue doing that. And then one person reports back when they finally find the exit. So that's the equivalent of what's going on over there. So your objective is to solve this thing. And yes, it does look like it's 45 lines, but I had a lot of white space, like a lot of white space in there. And you'll notice that basically over here that, yeah, this was just I also had a lot of white space over here. So it's not as intimidating as it looks. So that's going to be your homework. So again, you're going to get all this. And then I'm going to give you a bit more of a write-up, plus I'm going to have a review video that specifically goes over this stuff so that you know, so that basically it won't be something to be intimidated about. Again, when you're always being subjected to a new assignment like this one, I'll be honest, you're being my guinea pigs so for the future. So again, if you guys need to cry uncle so that I know that I need to give you more time. Okay, so. That's stacks and that's queues. Told you that they would be really quick chapters. But they're really easy to understand now because you understand what lists are. Okay, so let's go ahead and talk about the rest of this semester, even though that's pretty far out to be thinking. First, we'll be thinking the next data structure we're going to be tackling is trees. But before we can understand how to get through trees, we have to talk about recursion because trees are a recursive data structure. As we're going through recursion, we'll also go through recursive linked lists. In other words, we'll look at linked lists again and we'll be reviewing them as a recursive data structure. So just another legitimate way to look at linked lists. Some might say it's a bit more of an elegant way to look at a linked list, just to help us with both recursion and reviewing for linked lists. Once we do that, we'll get into trees, and then we'll get into hash tables after that. So. Let's see. Yes. Queues will not be on the test because I'm not really going to bother with it. Queues will probably be on the test for trees simply because they have interesting application or two on trees that you can't really see until you get a bit more stuff. Okay, so right now we're going to take a quiz. So it's should be the stack quiz. Its password is 11111. So that's 5 ones. Okay, it was being really unoriginal there. Two of the questions say they're quote essay questions. And my expectation for an essay is is for one of the questions basically a single sentence, and for the other one a list of 3 items. So it shouldn't be too hard. Basically, don't go into too much detail. Don't go into more detail than basically a single line of code. We'll resume here at basically like at 6:45, and then we'll get into recursion.